All right, welcome back from fall break. I hope it was a relaxing break from classes. I haven't got any questions about the exam or anything, so I hope also things were relatively resolved after stage 2 and the solution sets are out there. But if you do have any questions about the solutions, feel free to let me know and I'm happy to investigate further. So the schedule then moving forward here. So like I mentioned in the announcement yesterday, I gave you sort of a week off for the lab. So lab 7 is effectively a 2-week lab, even though it really is only 1 week of material. So lab 7 from last week is still this week. So that'll be due this upcoming weekend. Then next week is when we move on to lab 8. Lab 8 basically is a data collection lab where I will give you a bunch of data sets that are sort of from realistic data sets actually maybe real data sets, and we are going to be using what we'll be talking about in the lecture for input modeling to then come up with good input models for these data that I give you. And then the week after that will be a data collection week with your team. And so there won't be any formal lab the week after lab 8, but that will be time that is available to you to spend because you've got this input modeling report where in that input modeling report, you're expected to go out and gather a little bit of data on some of the inputs that'll go into your system so that you can then start understanding what inputs you need and then show that you have the ability to put some input models on there that make sense. And so lab 8 is really meant to kind of be practice for what you're going to be doing as kind of your first technical deliverable with your final project teams. And then after that, lab 9 and 10 are on a regular schedule. And then there's, I think, 2 open weeks after that that are meant to be, again, provide extra time for you to work on your final project. So that's kind of the lab and project schedule moving forward. So let me just double check here why this isn't advancing. The final project is posted. So in the final project, you're going to be getting in groups of nominally 4, but 3 is sometimes okay. But if you propose 3 group members, I may have to add a member depending on how the logistics all work out. In the end, if there's some people left over that couldn't find a group. So, so 4 is nominal and is ideal. And the idea is you'll get together and you'll look for a real world system. A lot of times people choose, we get a lot of coffee shops and restaurants and fast food places and things like that. But it's great if you've got something that maybe moves out of those kind of service spaces. So sometimes we get people that say, well, this is my dad's guitar factory, or this is something that I got involved with through my capstone, or this is some other relationship I had, or this is a bank, or something that it may that it's always nice to kind of spices up the kind of portfolio of projects when we have a few more of those that have other types of elements in it. But we just generally want you to pick a real world system, and that real world system you want to sort of identify and a potential operational challenge or optimization that could possibly be made that you could experiment with using simulation. And so that's the kind of basic idea as you're going to go out into the real world system, try to build a model of the salient features of that system, show that your model matches the current system, and then show that maybe proposed changes that you make in your model lead to or don't lead to performance differences, which then would provide data that for the actual stakeholder as to whether they should make these changes or not. So that's kind of the idea here. So if you look in the bank's book, chapter 9, exercises 1 through 5, they actually have a bunch of interesting kind of examples. Might be giving it, get your mind moving about like what types of systems you could look into. So that's maybe a good place to start. Otherwise, if you were to like walk around the ASU campus, I'm sure that there are a lot of different systems that you've probably thought, gee, this probably could run a little bit better. Like there's a particular coffee shop on campus that always has a long line. Is there something special about that coffee shop that could be changed that might alleviate that. Of course, what you want to try to avoid are the systems where you don't really need simulation to propose an answer. So if it's just something as simple as, man, they've got 2 cashiers working, they really need to do 2, or they've got 3, they've got 2 cashiers working, they really need 3. If it's just a simple queuing problem, you may not need to run a simulation to investigate the change from going 2 to 3. Or if you propose that sort of change, we know that by adding another resource or adding more resource capacity, we know that's going to improve system performance. But is it going to improve system performance enough to compensate for the cost of that other resource? So if that, what is enough is hard to answer without simulation, that's great. So then you can say, all right, so in order for us to really investigate this, we needed to run it in simulation in order to really quantify the change here, because we know there's going to be improvement, we just weren't sure how much. That might be okay. But we try to look for something that's a little more complicated, where it's just simply increasing resource capacity is kind of like, well, there's probably other tools that would help us analyze that. Something like changing the flow of things. And so instead of having, one line, maybe they have 2 in parallel, or, or the 2 in parallel that they do have, maybe we actually can look for synergies where we're going to maybe cross-train someone to work on both, or something like that. Like cross-training is another, a great one to play with. And you'll actually see cross-training implemented, I think, in Lab 9 or Lab 10. And so there are, those are the types of things I'm kind of looking for. Something hopefully a little more exotic than we just added resource capacity. And then, like I said, nominally 4, or ideally 4 members. You can propose 3, and that might be fine. But in the end, if there's 1 or 2 people left over who couldn't find a team, I may need to group them in with some of the 3-person teams. Where to find members? Of course, if you go to Lab, you can find them there. Post a Canvas discussions. Hey, I'm looking for a team member. Hey, we've got 2 team members. We're looking for another 2. That would be a great place there. I've also linked a Google spreadsheet, both in the final project module and in a recent announcement, that you can add lines to, where that's kind of meant to be a clearinghouse to say, I'm looking for a team, or I have a team and we're looking for members. And so you can go ahead and add a line to that and then come back and check it back later. You can put your contact info in there and then link up. And so we've got, I think, a little under 2 weeks to maybe like a week and a half to get this thing kind of done. So make sure to be looking for those team members as soon as possible. Then what do you do once you've got this team? So the first deliverable is, like I said, this names of team members. So that every single team member will submit an assignment where you tell me who the 3 or 4 people in your team, your team is. And so every single person does that. That way I can confirm that everyone agrees on who's in their team. And then most of the rest of these things are group stuff after that. So then you'll have this input modeling report, which will be a group assignment. And that's basically going to be 1 or 2 pages where you tell me what sort of system that you're interested in studying, what are the key problems with that system that you're kind of going to be studying there, and what are the inputs that you think you need, and what's some example input data that you've gone out and fit to show me that you've worked in the system, so you have kind of a more fine-grained understanding of that system. And there are details on what that input modeling report should look like online, and as well as a few example reports from previous semesters. Then there's a lull, and sort of toward then the last week of classes, there are oral presentations, which we a long time ago used to do in class, but now for a number of reasons, I instead have you record these offline and upload. And so you won't be presenting live, you'll be uploading one. And then after uploading to Canvas, you will then be assigned, every individual person will be assigned one other group's presentations to watch and then do a peer review of. So you'll have a rubric and you'll leave some comments. And it's a similar thing with the reports. And so you'll upload the report at the same time you upload the presentation, and then you'll be assigned a report to read. And the reports are just these 4-page reports. So every group is responsible for a presentation and report, and every individual is responsible for peer reviewing one presentation and one report. And then I will look at the peer reviews for the presentations and the reports, and I will combine those with my own assessments to determine the actual scores for everyone's report and presentation. So that's kind of how this is organized. So any questions about basic structure of the final project? And there are a lot more details on Canvas, what the report looks like. Again, I can tell you right now, it's like a 4-page report. It has a very specific structure. It's going to be easy to burn through those 4 pages very quickly. Similarly, the input modeling report, there's certain things we're looking for there, and that's detailed on Canvas. Okay. And this is, so yeah, in the presentation. So the presentations that you upload, they're just going to be 10-minute presentations. So there's an evaluation form and rubric that you can already see on Canvas if you want to see how they'll be evaluated. Written report, again, very specific format on Canvas, the 4-page, and then again, I'll use the peer reviews to help me determine what the final scores will be. And yeah, so try to get your team together ASAP. All right, otherwise, there's an ICA that's available for this unit. There's this homework. I haven't quite updated it yet, so very soon I'll release this homework, so it'll be available. I just need to update the numbers from the last iteration through. And then this, I think, is an old bullet because this used to be before fall break, but we made that change. So forget about the thinking about your final projects over fall break, but do form your teams ASAP. All right, so any questions about admin stuff? I'm also gonna see if online there's a couple of questions. So there's some questions online, a question about Lab 7, trouble finding information for the entities and project elements from the 5.7 section. So the question about Lab 7 online, it's difficult for me to address without looking directly at it. So if you would email me, I can get back to you. So when I have Lab 7 right in front of me, so I can maybe better address that. So if you can send me the details in an email, I'd be happy to take a look at that offline. And then there, Amy Cook says that her group is looking for 2 more people. And if any student sees this in the chat and is looking for a group as well, let her know. So if you would like to be one of the 2 other spots in Amy Cook's group, then she would like you to know that she has those spots available. And I think that's all. So any other questions about this sort of stuff moving forward? Okay. All right, let me make sure that I'm in screen. Yeah, all right, weird. Okay, so so where were we last time? So we ended the pre-midterm stuff talking about random variate generation, and kind of this all culminated in this inverse transform generator stuff, where if you know the CDF, you can calculate the inverse CDF and can use it with uniform random numbers to generate draws from any random variable that you would like. And so as an example, you know, if I give you a PDF like this one, then you can do a little integral under the PDF and all of the different pieces. And I won't go through details here because you guys are on the other end of this anyway. But after doing this integration where basically, you can even kind of think of this geometrically, it's like in this region here, it's the area of this triangle plus this growing rectangle where the rectangle's height is 1 and its width is x minus 1. Then you get, you know, like for this region here, this CDF here, which is the half from that triangle plus the x minus 1 width times the 1 height. And then that's how you get that portion of the CDF. And so we can end up assembling a CDF for these different regions, for the region from 0 to 1 and 1 to 1.5. And then we could invert that CDF by setting our R equal to the CDF in those 2 different regions, inverting that, and we end up getting an inverse transform generator like this one right up here. So this is the kind of inverse transform generator out of that. So if you're looking for another example of that, you could just double check that, you know, or exercising that double check that if you solve that problem on the previous slide, you end up getting this here. And once you get that, then we know that we can go into any computer program that gives us randomly generated numbers between 0 and 1, and we can then plug those numbers into this formula so that we then get X variates out. And so if I was going to Excel, I could create a column that generates a random number, say a column A, and then in column B, I could set up a little if statement where I use these conditions to tell me which formula to use here. So I can say if I am in the top row, then I do the square root. If I'm in the bottom row, I do the addition. And then I can fill those down to give me my two different columns, my A column, which is just my random numbers, my B column, which is my random variate, generate 1,000 of those things. And after I do that, I can then see what I get out with a histogram. And so now there are a bunch of different ways to generate histograms in Excel. I document kind of the old school way to generate histograms in Excel here, where you use the frequency array function in Excel to generate frequencies, and then you can use a bar plot for those frequencies. But now in modern Excel, you can just highlight the column, go to insert graph, and then it's got histogram as one of the stock options. And then you'll end up getting something that looks like this. And so we were expecting a trapezoidal PDF, and we get a trapezoidal histogram. So it lines up right on top of that as expected. So that's good. If I didn't want to do this in Excel, I could also do it in Matlab. And so similar sort of thing, I draw 1,000 random numbers. I generate a vector that's going to store my variates, and then I assign to, for every position in that vector, which has a random number that's in the top row, I use the top row formula. For every position in that vector that has a random number that is in the second row, I use the second row formula. And then I can generate a histogram of what I get out. I can play with the axes and everything. And then I likewise get a trapezoidal histogram out. Of course, the bars are going to be slightly different because Matlab used a different random seed and maybe a different random number generator as Excel, but the basic shape is the same. And so, I could in Arena do the same sort of thing where I could have a simple block like this one. I create an entity. That entity goes through an assign block called trap delay. And then in that trap delay, it first assigns RA as Arena's version of rand. It assigns a random number to R. And then in this trap delay assignment, I do the same thing I did in Excel and in Matlab, where I basically say, if I'm in the top row, use the top row formula, or if I'm in the bottom row, use the bottom row formula. That all gets assigned to some variable called trap delay, which I can then use a little bit later. So I can then say delay my entity by this trap delay amount right there. And so I can do all of that, and then I can actually generate a histogram inside Arena. And you can, Lab 7, you've got a bunch of different visualization elements, and this is one of them. And so again, get this trapezoidal histogram. The visualizations in Arena aren't that great, but they're really meant for you to just do a real-time kind of sanity check to see if everything's working. So, so this is, all of these things that we now can do. And of course, I could, if you're looking for another example, I'm not going to go through it, but you can do the same thing with the trapezoid the other way. And this is just me kind of going down through here and doing that. Now, if I've got a desired PDF here, and I've got an actual histogram here, which I am hoping looks like this desired PDF, then a question is, how do I really test to see that the numbers that come out of here are really a good fit for what I expected here? The math tells me that this should have worked, but what if I just wanted to check that? Or what if I didn't know ahead of time that there was a mathematical connection between this PDF and these data? Now, we knew from before the midterm that if I was given something that was said to be uniform, I could use a tool like the chi-squared test to see, is this really uniform? So this is what I think it should be, this thing down here. But it came out here and it's got a little bit of jagged edges. At what point are these bars too high for me to not be able to say this probably came from a uniform distribution. And the chi-squared test and the KS test help me solve that. And so what I want to do now in this section is to extend the chi-squared test so that we can ask the same question of this one here. So if I have a hypothetical distribution down here, and I get something out here, which at least looks like it passes the visual check, it looks like roughly that it's there, how do I add statistical certainty here? So I go out into the real world, I gather data from my Starbucks or my wherever, a cup of Joe or something like that, and I get something that looks like this. I look at that and say, that looks like it's this trapezoidal distribution, but how do I then add statistical rigor to that? So we are going to learn how to modify the chi-squared test and the Kolmogorov-Smirnov test so that we can apply them to these data sets to test for these hypotheses, as opposed to what we've already been doing, where we test for supposed uniformity. That's the first thing that we're going to be doing. The other thing, though, we need to do is how to pick these things to begin with. And so sort of before we even can do that chi-squared test, the Kolmogorov-Smirnov test, we have to be able to have some insight where we can look at a data set and we can say that data set is likely this distribution or is likely this shaped distribution. I may not know exactly where the corner is. I may not know some other details here, but I at least know it's this family of distributions. And likewise, or maybe I look at it and I say it's definitely this family of distributions. And so before we can even apply the chi-squared test to see how well we did, we need to figure out what's the family, what are the parameters, and then we can apply the chi-squared and say how good is the fit. So that's really these 3 lectures in the input modeling. It's that's the way you could kind of cut them down: is what's the family, what are the parameters, how good is the fit. And so that's kind of what we're doing here. All right, so before we move on to new stuff, are there any questions about any of this old stuff or about the inverse transform, any lingering things from pre-midterm material before we move on? We've sort of moved on into, this is the stats heavy section of the course, whereas more of the probability heavy section of the course beforehand. Okay. All right, so so let's think about a motivating problem. So we've got an arena diagram like this. This is our model for a very simple kind of security check at an airport or at a government building or something like that. So passengers arrive, they go through a process which delays them as they get checked for proper identification. They may have to queue up there. Then some of them will end up being cleared and the other ones will end up being denied. And so these are the 3 things that we're going to model stochastically. So random inter-arrival times, random times it takes for each one of their IDs to get processed, and a random set of them to get cleared versus denied. And so if we focus on the arrival process here, then as we've sort of talked about here, then we, this is maybe a real arrival stream where there might be some average time in between each one of these passengers. And let's say it's 20 minutes, but we know that the inter-arrival times are never exactly 20 minutes. Some are going to be less than, some are going to be more than, et cetera. So the stochastic approach here is we are going to design the right mapping of die rolls. That's what an inverse transform method does. So that when we roll the die, we end up getting some of the outcomes being less than the average, some being more than the average, but the statistics from our die roll are going to match the statistics from the real world. So even though we don't know the real world reasons why these passengers sometimes take longer to arrive in between and sometimes take shorter, as long as we get the statistics to match, it doesn't really matter if we've got it right there. And so the hope here is if we choose an exponential distribution, for example, then we might have a histogram of inter-arrival times from the real world, and we'll fit an exponential distribution to it, and it'll land right on top of that histogram. And then we can then wash out all of those real world details and just replace them with this nice clean histogram, which, or nice clean exponential distribution, which just has a single parameter. So we've now gotten rid of all of the real world details and just replaced it with a single parameter, 19.88, the average value for this here. So just by knowing the average inter-arrival time, we can now go into Arena, and Arena will naturally generate inter-arrival times, which are sometimes lower, sometimes higher, just like the real world, and hopefully generate data that looks just like real world inter-arrival data. So we now, if we feel good about our exponential distribution with this parameter, then we can go into Arena and we can say, all right, for this passengers arrived to security, we are going to set it as an exponential inter-arrival time with this average in seconds. We'll let it go for an infinite number of arrivals, and Arena will run. And so Arena will generate our inter-arrivals. It'll get pushed through the process that we've built, modeling the whole system. And then we come out of the system and we look at stats. So, and those stats then tell us how often did people have to wait in line, for example. So these variation we got on the output comes from the variation we put on the input. I mean, there's no other source of the variation. The input models are the source of the variation. But so if we choose the right variation on the inputs and the right structure of the system, then we'll end up getting outputs which are meaningful, which actually will represent outputs we'd expect in the real world, so that we can then experiment with the system and look at the changes in outputs, and then hopefully be able to make a conclusion that'll be valid in the real world. And so if we choose bad input models, even if we've got a good system, we're going to get bad variation on the output. And so this is the so-called GIGO property, garbage in, garbage out. No matter how great your stochastic simulation model is, if the input models you put in do not match the input variation you see in the real world, then the output variation it'll be variable. And sometimes variation is enough for people to say, hey, that looks kind of realistic. But the statistics you get on the output will not be anywhere close to the statistics you get in a real system. And so conclusions you make about these statistics end up maybe not being totally valid. And so you might say, oh, for these types of inputs, so maybe you didn't put an exponential here, you put a uniform distribution or a normal distribution. If you really did have a normal distribution of inter-arrival times, if you made this change in the security process, you would get some favorable outcome here. But in reality, there's exponentials on the input. And so that change may not result in the same thing here. So like in lab 6, in part 1, I had you generate a really simple system where you had to create 2 process blocks and a dispose. And I had you generate different distributions for those 2 process blocks that all had the same average. So the average behavior should have been roughly the same. And what I hope you saw is by changing the distribution shape in each one of those processes, you got different outputs. And so that's kind of an example of this GIGO process, is that even if your averages are correct, if the shape of the distributions are wrong, you can't trust the outputs that come out of it. And so that's why input modeling is so important, because it's really what's driving all of the variation we get on the output, is whatever the correct variation is that you put in on the input. So that's kind of how we're being motivated here by. All right, so any questions about all this, about what I mean by input modeling? After the midterm, everybody feels confident with this term that the inputs are not the system itself, they're not the entities themselves. The inputs to the system, the dough that's being fed into this system and being shaped by it, is actually the variation that you design as your model of the input variation. So these probabilistic models are the inputs going into these systems. Okay. All right, so a little cartoon just kind of summarizing this same sort of everything I've kind of been saying here. I did the analysis, the engineer looks at the boss, and I did the analysis using your bad assumptions. So bad assumptions, those are the bad inputs. Then I applied your flawed logic and arrived at a predetermined answer. And so this is an example where with the right assumptions, you can get pretty much any answer that you want. And then, so that kind of shows that it's really important to make the right assumptions. And then should I begin disillusioning the team, this needs a pie chart. So, then you can add, if you've got a pie chart with a lot of variation there, you can end up actually distracting someone, because they can say, look, we did get variation on the output. So this is a realistic system, but it's not the right variation. So really it's the assumptions are the input variation going in. You got to get those right so the output variation coming out is reliable output variation. So that's what this whole section's about, selecting the probabilistic models that mimic our realistic variation. So for queuing models, we're going to be choosing interarrival times and service times very often. For supply chain models, we're going to need to choose the right input variation for demand and lead time. So the amount of time it takes for when you make an order for that order to then come filled. For reliability problems, we'll be choosing input models for failure times. And so this is, you can mix and match all of these, but this is basically the types of input models for these kind of three major categories of systems that we work with. And this is just me beating this over the head, is that we need to make good choices to make good inferences and good recommendations. So we are going to talk through lectures G1 and G3 about collecting data from the system, about identifying the right family, parameterizing the family, and then assessing goodness of fit. So that's the flow through here. So let's talk about collecting data, which is something that you're going to start doing, well, you're going to sort of pretend like you did next week for whatever that lab 8. And then in the week after that, you're going to actually collect data for a real system. And so when we think about collecting data, we have to sort of ask, when do we need to collect more data? And when can we use data that's already available? Available data is sometimes great because it really can make things a lot cheaper to, it's great if you can say, well, somebody's already collected all the data for us, but you have to be really careful with data that people have already handed you, because there might be a bunch of reasons why that data is not relevant to the modern study. So here's kind of an example of that. Let's say we were tasked with investigating how to reduce time patients spend in a clinic. So the entities for this model are the patients. They're the ones that are getting delayed. The activities include nurse obtaining patient history. So nurse is a resource, and it takes her time or him time to obtain a history from each one of these patients. So there's a prior study from 2002, 20 years ago-ish, that already collected timing data on nurses taking patient histories. And that data is still available. So your stakeholder looks at you and says, well, in your budget, you've budgeted so many $1,000s to do this study here, but fortunately, you don't have to do that study because we already did that study 20 years ago, and we're going to give you that timing data so you don't have to go out and do this, this study again. So should it be used? So what do you think? What are potential problems with using, for this particular system, this 20-year-old data about nurses taking patient history? Any thoughts about whether the timing data from 20 years ago, why it might be different today? Yeah. Right, so technology would be a big thing. So when, over my lifetime, I remember when I was a kid, when you went in, I mean, everything was done on paper. And so you go in, a nurse would take your history and there would be a form and they would fill it all out and they would write it and everything like that. And then gradually over time, things have been shifting to a variety of different ways of automation. So there were tablets maybe that got involved, or computers on wheels that are rolling around. Even in the computers, it might have started out where everyone had to type things out, but then they got codes where the common reasons why people were in were already coded in there, so that you could just type in a quick code and then you don't have to put in all of the details over and over again. So 20 years ago, this activity of taking patient history was a totally different activity. So if you were to use this data, you would bias your study, because this data would end up maybe taking a lot longer in this portion of the simulation study for the nurses taking the patient history. So that's an example of where, even though data are available, these data are really for a totally different system. It's not for the modern system of this here. So that's one kind of example. The other thing people will tell you, your stakeholders will tell you, again, usually to keep you from running a study, is summary statistics. And so let's say I have a simulation study that wants to assess the impact of new security protocols being implemented on metal detector feeding a government building. And so again, entities, people, the activities are the time to pass through the metal detector. So I want to run this study, and 1,000 observations of time to pass through the metal detector are recorded. And then before looking at the distribution, it's noticed that the mean and standard deviation are nearly identical. So when the mean and standard deviation are nearly, just looking at those summary statistics, mean and standard deviation, that can give you an idea of what might be a good distribution to pick. And so, we could say, well, what distributions are out there that might have a mean and standard deviation that are identical? And if we think about that, the exponential as a one parameter distribution whose mean and standard deviation are both basically the same. It's 1 over lambda in both of those cases. And so we might look at that and say, well, just based on the summary statistics, the mean and standard deviation being identical, this has got to be an exponential. Without even looking at the histogram, it's tempting to say that. So then we look at the actual mean, and it says the mean passage time is 30 seconds. So then we can say, well, imagine if it's an exponential with 30 seconds as a mean. That means that there are quite a few passage times that are going to be less than 30 seconds, but there's quite a few that are going to be way more. But 30 seconds, the average here, already seems to me like this goes against my my personal experience with metal detectors. So we're just talking about the time it takes to walk. If the metal detector is this set of floor tiles, it's the time it takes to walk across that set of floor tiles. That's what we're talking about here. And so it's even 30 seconds, it just does not seem like a normal metal detector for me to think the average person is taking 30 seconds to cross across here, where there's some people taking a little bit less than that, and some people taking way more than that. So imagining a minute to cross this floor tile, the section here, it just doesn't feel right. So that's kind of a red flag that we have here. So if I look at the actual data, I see that it's bimodal. So there is a group of times that are very short, let's say 5 second average, and then another group of times it's very long. And so this is definitely not exponential. And it starts to feel more like something that makes sense for a metal detector, that there's a group of people that just pass through the metal detector. We still have to try to deal with this second hump though, but at least it starts making a little bit of time or a little bit of sense there. So, so that's our first iteration through here. So we have this model where we had a very simple passage time that we're trying to model with a single distribution, and we find out that that single distribution we need to use is bimodal. So I need to modify this to deal with this bimodality. But before I do that, are there any questions about what I mean here? So I look at the data, and instead of the data being, next second, maybe flip on instead of the data looking, well, I'm not going to find it in time. Instead of the data looking like an exponential, straight up and down, it's got a sharp peak at short times, and then it's got another peak at long times. That makes sense. All right. So I look at that, at bimodality, and then I think, all right, well, then maybe what I need to do is break my system diagram up so that I can better capture this bimodality within the structure of the system. So what I'm going to do here is I'm going to say, I don't have one input model, passage times. I have 3. I have a long passage time distribution, the upper mode, a short passage time distribution, the hump that's the lower mode, and a probability of triggering the detector, which my hypothesis here is going to be what determines who's in which mode. So the idea here is that maybe what I'm actually seeing here is that there's a group of people who pass through the metal detector and keep on going. Another group of people get flagged by the metal detector, go back around and have to pass through the metal detector again. But if I'm only taking data, keeping track of when someone goes in and when they come out, then all of this looping that's going on every time they get flagged, I'm missing out on. And so that's the reason why just looking at people going into the metal detector and coming out of the metal detector ends up generating this bimodality where it looks like some take a very short amount of time and some take a really long amount of time. But I'm really, the people that are taking the really long amount of time are cycling through the metal detector. And so under that hypothesis, then I actually need to break my system up into these things where I've got a probability of who's going to be in which group, and then a passage time for one group and a passage time for the other group. So that's the way that I'm modifying this here. So are there questions about, does that make sense, this revision here? I saw bimodality, and rather than me trying to fit a bimodal distribution, I said, well, I'm gonna split that distribution up into two distributions, separated by a decide block, a probability. And we'll actually do this in a more complicated example next time, where actually I'll build a diagram that does this. And then from those two groups, I can now have a simple short passage times distribution and a simple long passage times distribution, which I decide who gets which one of these distributions based on that probability, that decide block. So that's how I'm restructuring the system to capture more of the reality of the dynamics of how it works. All right, so now that I've solved the bimodality problem, I now can deal with that in my data. I look at my data and I see that passage times are negative. Some of them are negative. And that doesn't make any sense at all, because passage times should never be able to be negative. So at this point, I, looking at my data, have to make a decision. Can I fix this? Is there a calculation? Like maybe when the way passage times are calculated, maybe someone left out a particular factor or something like that. And so things didn't always subtract the way they should. And maybe I need to fix that calculation. Or it could be garbage data. It could be that I had somebody keeping track, maybe the person who had the stopwatch for leaving the system, maybe they just transposed a couple of numbers and I don't know which numbers those were, and it's just totally junk data coming out of that, and there's no way I can fix it. So I could decide to just discard those. But if I do that, I needn't have to worry then about, will discarding this data, will it create any bias of any particular way? So, there are ways that we can accidentally bias our input model. So as an example, if I'm talking about failure time data for lights in this room, then I know that that I'm in this room for 75 minutes every session. So these lights live for at least 75 minutes. I don't know how long they live after I leave the room. I don't know what was before that. So if the lifetime of the bulb is greater than 75 minutes, that's kind of hidden to me. And so by censoring my data so that I can say that, well, I never have seen a failure time longer than 75 minutes, then it's going to bias my distribution of the actual failure times of these things. So I have to be careful that whenever I don't have data, how does that affect my parameter estimations? And if I throw out data, am I going to accidentally bias my parameter distributions? If these are truly garbage data, I'm not going to create any biases. But if I accidentally notice that it's only the long passage times that tend to somehow get corrupted by the process. And so maybe whenever the person on the input side calls out a number, because they've called it out like in a walkie-talkie, the person on the output side is unlikely to get the number wrong if it's close to their number. So maybe that's going to mean that the garbage data are never going to be the short passage times, but they are very likely to be the long passage times, and the two numbers are far from each other. And so when you call it out over the walkie, then maybe the other person gets confused if it's doesn't quite match. So if that's the case, then I need to really be careful, because I need to get rid of these data, but I also somehow need to account for the fact that I'm going to have way more data on the short passage times than the long passage times. That's going to affect my probability of triggering the detector. So these are all practical issues you have to think about as you start working with these data sets. So yeah, that's all I'm sort of saying there. So are there questions about that example? Is it clear what I mean by accidentally creating bias if these corruption processes might only happen, let's say, with one particular aspect of your system? And so you actually think you're fixing the times, but you're actually now adding further corruption to the probability. So the only way we can get around that is either by estimating the frequency of the corruption and trying to uncorrupt that, or maybe going out and just taking more data. So, so that's just something you really have to, it's just realistic. There's not like a one easy fix for these types of problems, but these are common problems that come up that you have to deal with as they come up. So gathering data is a really ugly business to be in. Okay. So, so one question then, so what can we do? What are good suggestions, good heuristics for gathering data? So as you start moving into your final project, with your teams, you start discussing the system that you'd like to work in. Before you even start gathering the data, just take a little bit of time to spend some time just doing pre-observation and planning. Visit the system and just try to notice what are the weird things that can happen in this system. You may not notice all of them, but you probably will notice a few things that you didn't notice before. That, oh, that's an error, that, you know, that's a failure type that I never thought about before. That, oh, I noticed that if I'm watching McDonald's or something like that, there's one particular day that somebody from inside the store came out and had to go through and tell everyone in line that the machines inside the store were down and they had to close the whole store until they got fixed. You're like, well, that's an event that I didn't anticipate, you know? And so there are all of these things that, you know, from your looking back on what, you know, when you weren't paying that much attention, there's all of these things that you may not have ever kind of burned into memory, but now that you've done your kind of pre-observation, you can say, okay, these are potential issues that could come up that we need to make sure that we're gathering enough data for. Now, once you start gathering the data, you have to be really careful about this because you don't want to bias further data gathering. But what you can do is, as you're gathering the data, is just do a little bit of analysis as you're going. You're going to ask me, I know that a bunch of groups are going to ask me as we get closer to the end here, how much data is enough? And that question is going to be different for each one of you because it's going to depend on how much variance are in your system. If every single inter-arrival time is very close to, you know, 15 seconds, then you don't have to take a whole lot of data. You'll be able to say it's very close, it's 15 seconds of very little variance. But if every single inter-arrival time is, you know, has a huge amount of variance, you're probably going to have to take a lot of data on inter-arrival times to really get a good fix on that distribution. And so you can look at the data while it's being collected, and you might find that there's so little variance that actually your efforts are better spent gathering other types of data. Or you might find there's so much variance that you need to budget more time to be taking more data. So it's worthwhile to sort of look for these kind of red flags and make those changes, as opposed to just taking all the data and then after, the day before you're going to do your final presentation, then analyzing it and finding out that there's no way you can get like a good fit on the little bit of data that you have. Something else you can do is to look for what we call homogeneity and combine homogeneous data sets. What do I mean by that is if you go to an airport or something like that, you might find that there's that I don't need a separate airport model for the Monday inter-arrival times and the Tuesday inter-arrival times. That Monday and Tuesday are effectively the same. Like if I look at the distribution of inter-arrivals on Monday and I look at the distribution of inter-arrivals on Tuesday, they look identical. And if that's the case, you can pool, so combine, P-O-O-L, pool all of the Monday data and the Tuesday data together into a single weekday model. And you can just say, as long as weekday, I know the inter-arrival time. So I'm going to pool that together. And you suddenly will get a whole lot more data. So you'll get much better model fits and a simpler model, because now inside Arena, you don't need to say, is it Monday? Is it Tuesday? Is it Wednesday? You can just say, is it a weekday? Is it a weekend? And you can just flip back and forth. So look for those sorts of things there. It's at a higher resolution too, hours. Like, so you might find that there's a huge difference between 9 a.m. and noon and 5 p.m. Those 3 hours are totally different inter-arrival times, service times, or whatever. But 9, 10, and 11, all three of those hours look pretty much the same. Noon through 4, those look pretty much the same. 5 through 9, they look pretty much the same. So then just create a model for morning, a model for afternoon, a model for evening, and pool all of the data that you've had in those three groups together. So that's what I mean by pooling data. That's a great way to increase the amount of data you have for the models you're building and greatly simplify your model. And then I talked about data censoring already. So observations might start after a part has been in service. Observations might end before all parts have failed. So this can bias failure distributions. So you have to be very careful about censoring generating bias. And so in statistics, there are all sorts of, if you take more advanced statistics courses that go into estimating failure time distributions, you'll learn about survival analysis. And survival analysis is just a fancy way of saying fitting exponentials when your data are likely censored. So if you ever hear that term, survival analysis and Cox proportional hazards and all that sort of stuff, these are just fancy ways of saying we really need an exponential distribution, but we knew that our data are probably not going to be over a long enough window for us to capture all of those failures. And so it's dealing with the censoring problem. All right, and then and the last sort of tip on here is look for relationships between variables. And so this is someone that is often forgotten. So I might have, I can take all of my inter-arrival time data and all the customers that correspond to each inter-arrival time. I can also look at their service times in a simple one server queue. And I might get a scatter shot like this. So every customer, this is this customer's inter-arrival time, this customer's service time. And in this particular, and these are the marginal distributions. So the inter-arrival times looks like this hump, the service times look like this hump. And if I look at this, I see no correlation between the two of them. Now, I might have instead, for a different system, plotted that, and I get the exact same marginal distributions, but notice here it's a cigar shape. So when I look at this, it tells me that there's actually a relationship that for whatever reason, I don't know the cause, those that arrive very late after someone else, so the long inter-arrival time, tend to also have a long service time. And those who arrive very short after someone else tend to have a very short service time. And so this tells me here that although it looked like I had two independent variables, maybe actually I could get away with using the inter-arrival time to predict all or at least some of the variance in the service time. So really, I only have one variable or somewhere between one or two variables. And so those correlations can be really important. I mean, you can think operationally, it's really important to know that, I mean, this is a very different operational setting than this one over here. Over here, you know that the long service times somehow, like, it's almost like maybe your servers are getting lazy, because it's almost like when there's a huge gap in between customers, then the service times, it's like people need to warm up or whatever. But when there's a short gap in between customers, the service times are low. So this is a very different operational case than here, where in here, it doesn't matter what the inter-arrival times, the service times are always the same distribution. So it's really important to spot these things because it has major operational consequences. Now, what can you do? There are some sophisticated techniques like NORTA, which is normal to everything, which is a way of creating these correlations. So you can actually create two random variables that are correlated with each other. But a simple thing you can do is to build a little statistical model where you say, okay, I'm going to just fit a line through this, and that line's going to have a slope of 2.5. So if I know my inter-arrival time, then I just multiply by 2.5 to get my service time. And I'm going to add a little bit of noise around it, which has to do with this residual variance here. So I can build my own little dependent random variant, which just takes one random variant as an input, noises it a little bit, And that's what I get on the output here. And then I can then do a histogram of these things and see how well they fit this pattern here. And then that might be a real simple way to implement those correlations. And I can adjust this parameter inside Arena so that I can get rid of the correlation or make it a little bit bigger programmatically. So that's one easy way to do that. All right, so questions about that, what I mean by correlations between variables and approaches you can do to build models that implement those correlations. The biggest thing is to look for those correlations. If you're taking your data, then, I mean, sometimes, you know, you can't look at every single correlation. You can't do every single, scatter plot. But at least on some where you might sense that there might be something like that, then you can do this to try to at least see if there is, you know, if your intuition is correct. And if it is correct, then actually this can sometimes simplify your models, because again, it might mean using less random variables. So you don't have to fit two distributions. You really want to fit one and then choose a couple of parameters for the other. All right, no questions about that. Questions online. All right, so this other example implementations of this right here and how to build that in Arena. All right, so other things we need to look for, autocorrelation. So you're gonna take data and so you have sample numbers here, sample values here, and we talked about testing for independence. Well, there's a similar idea here is not only do we want independence in a random number generator, sometimes we want to know if our data are independent. So if we take a bunch of samples like this one here, do we know that there are absolutely no patterns in time over time here? So one thing you can do, which I kind of talked about before the midterm, is you can generate these scatter plots where you've got the sample value that you've taken in a time series, and then you've got the sample value, say 10 samples later. So from that same time series, just later, and you look to see if it's if it looks like a cigar or if it's a scatter shot like this one here. And if it's like this, then we would say that this has no correlation. So the time now does not predict anything about what it's going to be 10 samples later. And so if this were the case for every single lag, for every single, so 10 samples later, 11 samples later, 9 samples later, et cetera, then we would call this white noise. So the term white noise means that if you know the data now, you can't predict it at any time later. And that's makes it white. And so there's mathematical reasons why we call it white. It's mathematical reasons why we have other types of noise called pink noise, where pink noise means that you can predict things kind of nearby, but not very far away. So it has a little bit of a drift to it. So there are these color terms, but that you've probably heard before that have these more rigorous definitions here. So we can, you can generate these correlograms, and you can actually do this inside a tool of Arena. So you can give it a time series like this and generate this correlograms. And when you have patterns in data like this one, then this correlogram summarizes all of these cross lag or all of these auto lag correlation plots, so that you can see for a zero lag, you get the top correlation. For a lag of 400, you get a negative correlation, but you get some correlation and so on. And so for this particular time series, it clearly has a pattern. And so it's easy for us to see, and we verify that in the correlogram. It's sometimes hard to see the patterns here, but the correlogram will often capture those. So if you do the correlogram, then it'll show you that, you know, you may not have been able to see it with your human eye, but actually the statistics tell us that there is at a particular lag, so at like 150 or something like that, then there is high predictability. So knowing the data, the point at one point gives you a lot of predictability about what it's going to be 150 farther on. And so this tells you if there's going to be like bursts in traffic. And so, you know, there might be people coming to the store. If you start noticing that the inter-arrival times start getting clumped together, then maybe that tells you you're about to get a burst. And so that tells you that that short inter-arrival times end up producing short arrival times, short times after that, so that I need to kind of adjust things so I get these bursts in traffic. And so that might be what I'm showing here. So we need to look for autocorrelation as well when you're looking at these data. And so there are ways we can implement autocorrelation. This is getting a little more advanced. If you need to implement something with autocorrelation, you can talk to me about that in your project. But in lab 6, we do talk about schedules, and that's kind of the simplest version of that, where you can say at different times, you get different arrival rates, and you can just schedule that. So at 9 a.m., you get one arrival rate, 10 a.m., get another arrival rate, so on. And you can also do that with capacities. You can do that with failures and so on. And so schedules are the simple way to implement these patterns over time. But if you need something more complicated, we can talk about that on a case-by-case basis with your projects. And there are other ways we can implement that, which I'm just hinting at there. And I think almost done here with the data collection tips here. So I know this is kind of dull, but the other kind of important thing, and this will come up on the next homework as well, is the difference between input data and output data. And so this will be like a good final exam question, because this is like super important coming out of this class, is that input data are uncertain quantities beyond your control. So inter-arrival times, service times. But output data, you can still take output data, and you should take output data, but that output data, we don't view as inputs into those models. So the output data you just hold on to until after you've run your simulation. So for example, queue waiting times. When you go out there and take data, let's say you're taking data on a restaurant, a fast food place, you should definitely take inter-arrival times. You should definitely take how long it takes to actually make the food. And you should take times on how long people spend waiting in line before ordering. But that waiting in line before ordering should not go anywhere near your arena model. That's an output from your arena model. But then after your arena model runs, then you should then verify that the waiting times that come out of your arena model match the waiting times that you saw in real life. So we still take data on outputs because we want to validate that our simulation models produce realistic outputs before we can actually then make a case for using those simulation models. But you should not, even though you're taking waiting time data, you shouldn't be implementing that waiting time as a process inside your arena model. This is a very common mistake. People are going to say that, oh, well, I saw that they on average waited 10 minutes in line, so I just put a delay block in and did an exponential distribution or Weibull distribution or whatever for 10 minutes. And that's, you don't want to force that. You want to just look at how long they actually wait in the arena model and then compare it. Did they wait 10 minutes in your arena model? Great. If they waited 5 minutes in your arena model and 10 minutes in real life, then that might mean your arena model is missing something. So we use output data. We gather output data to validate simulation models, but we don't actually use it in the model. Does that make sense, that distinction between input and output? It might seem to make sense now, but this is like the biggest of the next month. This is like the biggest thing that people get mixed up, is that the models that you'll build, you're going to be really tempted to use output data, or you'll only take output data and you won't realize that you didn't actually take enough data for input data. So if you're taking data on when someone enters a restaurant and exits a restaurant, that's not enough, because that's mixing up the inputs and the outputs together. You need to know exactly how long it takes for their food to get made. How long did they spend at the table? So the time they spend, that way we know the difference between activities and delays. If you just say how long are they in the system, that's a summation of activities and delays. You need to separate these out so you have separate data on the activities, which will go into the model, and then data on the delays, which we'll use to judge whether it's a good model. All right, questions about that? Is that clear? It's like a major confusion point over the next month. I'll guarantee it. All right, and so that's kind of the last. These are kind of like our heuristics for what you should think about when you start gathering these data. So then what we're going to then do next time is saying now that you've gotten all of that data, hopefully all the right data, because you took all your inputs and all that and so on, then we need to start looking at the data. And we're going to use a histogram primarily to do that. There are more sophisticated things we could do, but we're going to start out with a histogram. So that sounds easy, but what's the bin size you need to choose for the histogram? Those sorts of things. Those are issues that we have to deal with. Once we have that histogram, we combine that with our physical intuition about the process. And that hopefully will give us an idea of what family from all of those probability distributions you learned about pre-midterm, which of those might best fit the data that we found. And once you've chosen one of them, then, and you might have used PP plots and QQ plots in other classes, we'll use PP plots and QQ plots to assess how good our family guess was. Once we can then zoom in on that family, then we can move on to lecture, then we can move on to fitting the parameters for that family. So we actually tighten it up. And then we'll finally have the distribution that we think is the best distribution that we could possibly fit for these data. And then we then can assess exactly how good it is. And so this might just be for our information. Like we really can come up with no better distribution, but how good of a fit is it? Because it only explains 60% of the variance in our data. Well, maybe that's just good enough. And we'll use the chi-squared and KS tests to be able to assess whether we've made some good choices and exactly how good those choices are, and whether it's worth trying to go backwards in the process, come up with a new family, or whether this is good enough for us to keep moving. And so that'll give us an opportunity to talk about things like how do p-values relate to best fits and so on. All right, so any questions about the timeline moving forward? Today was pretty much just a high-level overview day. I'm just hoping that some of those things sunk in, and as you start taking data out there, you'll realize that, oh wait, Ted said that we shouldn't just do when they enter the line and when they exit the food process. We really need to know when they hit that server too. So that way we can separate out the waiting time in line from the activity of ordering your food and then getting your food. So, that's like a super important thing: inputs versus outputs, delays versus activities. So questions online or in class? Okay. In that case, let's do the attendance question for today. And just putting the URL online. And so the question I have today here is, what is a continuous distribution whose mean is the same as its standard deviation? And otherwise, that's all I've got for you today. Things will be a little more exciting on Tuesday. And just as a reminder, Amy Cook wanted me to say that she's looking for 2 more people. And otherwise, there's a spreadsheet online you can fill out to hopefully, advertise whether you're looking for people to add to your group or looking for a group to join. Feel free to use the discussion, Slack, etc. as well. All right, so that's all I've got online, folks. So if any of you have questions, I'm happy to take them. Otherwise, you can feel free to head out. I'll be closing the room shortly if there are no other questions or comments. Okay, have a nice weekend all.